Okay, good evening everyone. So today is the first live session for the course Measure and Integration. So you already have seen the lectures what has been put on the website. So what I'll be doing, in the first half, I'll basically recall all the theories that you have learned, okay, and I'll give some insights to that and not just theory. And then in the second half, I'll just try to solve few problems based on that theory. Okay, so let's start with the theory. Okay, so you already actually saw in your lectures, that we want to generalize the notion of Riemann integration. That is the purpose of this whole course, right? This is what we want to do. Now the reason is, there are two reasons for that why we need to generalize this concept of Riemann integration. The first one is to enlarge the class of integrable functions. Okay, so I'll give an example which you already saw in the lectures probably, okay, which is not Riemann integrable, but it makes sense to give some sense of integration to that function. Okay, so I'll first elaborate this first point. Okay, so consider this function f of x. So let me first write this one. So suppose this q is the set of rational numbers and this 0 1. So obviously this is a countable set, so I can enumerate that with q1, q2 and so on, right? Now consider the function f of x, which is given by 1 when x belong to this q intersection 0 1 and 0 else. That is, if x is irrational in the interval 0 1, then we are taking the function to be 0. Now you already know that this function f, so this f is not Riemann integrable. And that is due to the density of rationals in real, because when you try to calculate this upper Darboux sum, so I am denoting it by u. See, if I try to calculate this u of f, which is the upper Darboux sum, so you'll get the value to be 1, and if you calculate the lower Darboux sum, you'll get the value 0, right? So clearly this is not Riemann integrable. Okay, but if you see this function, now you already know that this q intersection 0 1, this is countable. Okay, and this the 0 1 minus q is uncountable, right? This clearly means that the size of this set is very large, I mean at least larger than this one, right? This is there. Now you will see later on that actually the size of this set, now I am saying size, later on you will see you have already seen the notion of measure, so I am saying size just in a vague sense, so you'll get to know about the measure later on. Okay, so far size means just the size in usual sense. So you will see that the size of this set, okay, the size is 0, okay, for this set. Let me put an arrow here. So this size is 0, and therefore since the size of interval 0 1, size for the interval basically means the length. So we know the length of this 0 1 is 1, so the size of this one is 1. Okay, so this you will see later on, that if any countable set has a size 0 with respect to the Lebesgue measure, okay, that you will see. So here we are actually talking about the Lebesgue measure. Okay, so this means basically that the function f is actually 0 in this set 0 1. So this is 0 1 0 1 minus q, and you know that this is the set which is carrying all the size. The other set, which is q intersection 0 1, is of measure 0, so that is not playing any role if you want to talk about the integral. Okay, so that is why, since this function is 0, this means that the integral, so this is 0 on this, so in other words you can say that the function is 0 almost everywhere. Okay, now you will see what this almost everywhere means later on. but just for now you can see that this function is taking value 0 almost on almost all the points on the interval 0 1. Okay, this is what it means as of now, just in usual sense. And that is why you can see that since the function is actually 0, is taking value 0, so the integral, so integral basically means the area under that curve. So this would imply that the area of f, I mean area covered by this function f, the graph of f, will be 0. So this should mean that this integral is 0, although you have to make sense of this integral, which will be seen later on. So you can see that this integral should be 0. Okay, what this integral is you will see later on. This is not the Riemann integration. We know that it is not Riemann integrable. Okay, so this is that we want to include such functions in the set of integrable function. Okay, because you can see that it makes sense to talk about this integral. Okay, so this is the first reason why we want to extend the notion of Riemann integration. Now the second one is for exchanging the limit and integration. Now if you consider this sequence fn of x, which is 1 when x belong to this set q1 q2 till qn, okay, and 0 else, you can see that this fn of x converges to fx, okay, pointwise. So this is there, and this f is this one. Okay, so I am talking about this function f. Okay, so and you know that fn's are Riemann integrable. Fn are Riemann integral, and this means that this integral fn has some sense, and you can clearly see this integral fn is 0, right? So let me write Ri, Riemann integral of fn. Okay, so I am denoting it by fn 0, so it is from 0 to 1. Okay, so this is 0. Now since this is a constant sequence, this will converge to 0. Okay, but we know that the function f is not Riemann integrable, and so we cannot, does not make sense. So how should I write? Okay, so 0 1 f does not make sense. This means we cannot talk about this one, such thing. Okay, so this is not the Riemann integration of f, but we know that some integration of f is 0. I mean that we need to make sense of. So that is why, so this is equivalent to saying this convergence basically means, so I should write in some other color. So what we mean to say, that when limit of fn is equal to 0 1 limit of fn, when can we exchange the limit? In this case we cannot do so, that is quite clear, right, if we talk about Riemann integration. Okay, so with what integral? So I'm not writing this 0 1, so let us try to put this 0 1. Okay, this by this I mean some integration. Okay, so I want to make sure that when this limit can be interchanged, that is the whole point. We can see with Riemann integration we cannot do so. Okay, and you will see later on some theorem named as MCT, DCT, there's some generalized DCT also. So in such theorems you will see how when we can change this limit. Okay, so that you will see later on. So these are mainly the two reasons why we want to generalize this notion of Riemann integration. Okay, now the point is how to generalize this Riemann integration. So you already know. So suppose I take this function. Okay, so now suppose this is minus 1, this is 1, this is, let's say, half, this is, sorry, minus half, this is half. Now consider this function. So suppose it is taking value half in this interval, so let it be hollow. Suppose here it is taking value 1. Now you know, so this is my function f. Okay, so this is the graph of f. Now you can clearly see this f is Riemann integrable. Moreover, the integration of, and how do you evaluate this integral? So what we do, we basically partition this domain, right? We partition the domain to get the value, and then we pass the limit. So this is how we evaluate this integral. So the value of this will be basically half plus half, 1, then half, I think 3 by 2. Okay, so this will be the value of this Riemann integration. So on this interval -1 to 1, this is the value. Now the next goal is that we can generalize this to Lebesgue integration. Okay, so how to go for the Lebesgue integration, that I'll show. Okay, so let me write it here itself. Okay, so now here I'll define few sets. So suppose this is E of 1. Okay, now E of 1 is the set of points -1 to 1 where the function f is taking value 1. Okay, E2 is, let's call this E half, x belonging to -1 to 1, such that the function fx is taking value half. Okay, so these are the two sets, and you, in this particular case, okay, what this E1 will be. So this E1 is nothing but union of -1 minus half. Okay, and then you take union with half 1, and this will be -half to half. Okay, now then how to evaluate the integral? In that case, the Lebesgue integration. Okay, so the integral of f, so this I am writing -1 to 1. So by this I would mean Lebesgue integral. Okay, so this represents Lebesgue integration of f. Okay, this is the notation. So here what we do, we'll take the value of the function. So the function is taking value 1. Okay, and then we'll multiply with the size of E1. Okay, size of E1. The second value what the function take is half, and then we'll multiply it with the size of E half. Okay, so here what we are doing, we first try to determine the range of f. So the range of f is 1 and half. Corresponding to each of the value, we try to write E1, E half, and then we multiply the value of the function with the size of E1, right? So instead of partitioning this interval, okay, so now I should rub this off. So instead of partitioning the interval, what I am doing, I am basically trying to partition the range set. So we can see here the range set can be partitioned in two parts. This is singleton 1, union half. That's it. Okay, so we are basically trying to, in this particular example, the function f is taking just two values, and corresponding to that we are writing the sets E1, E half, and then this is the way how we define the integral. Okay, the point is, over here you know that E1 is an interval. Okay, so for interval, size basically means length. Okay, length of the interval. Okay, so that is it. For interval, size is nothing but the length of interval. So here you can easily calculate this thing. So here the size of E1, so size of E1 will be nothing but, you know how to determine the size of these two units. You will just, since these are disjoint, this is by the common sense. So far I am just talking about the common sense, that the size of this union this will be nothing but the sum of these two, right? So it will be half plus half, which is 1, and size of E half will be the length of this interval, which is half minus half, which is 1, right? So this is 1, and in this particular case you will get that this is 1 times, so the integral would be 1 times size of E1 which is 1 and then half, right? So it is 3 by 2, it's the same value. Okay, so this was easy to calculate. Now suppose you choose this function, okay, so let me write this function again. I'll just copy it from here. Suppose you had this function. Now here E1 is nothing but Q intersection 0 1 and E0, these are the only two values that the function is taking, is 0 1 minus Q. Now how to measure this? Right? Since this was interval, we knew some notions of measure size, that is the length, but how do we measure this one? And this is why this motivates. So we do it, and here we need the notion of measure. Okay, actually, okay, I'll tell you later on. So the length, okay, that I'll tell later on maybe. So this is basically the reason. Okay, so how to measure this one, and for this we define the notion of measure. Okay, how to get the size of this? It's better to write here, size. How to get size of this? Okay, because so this would imply, so because this would mean that the integral of f on the interval 0 1 is 1 times size of E1 plus 0 times size of E0. Okay, so this is the reason why we want to get some notions of measure. Okay. So this is what I have written, that we want to make sense of size of any set. Whatever set we choose, can we measure it or not? So that would be the question. Now what is the size of interval? As I have explained, the size of interval is nothing but length of interval. Okay, now every time I am saying length is something which is obvious to us, we already know these things. So let us see some properties of length. Okay, so what are the properties of length function we know? So I'll write it one by one. So we know the length of any interval. So I am talking about interval, okay, so far. So length of interval will be nothing but, what is that? So suppose, okay, so let me write this one. So length of any interval is nothing but greater than equal to 0. Why? So you choose any interval. So any interval will be of this form, or of this form, or of some half, or of this format. In each case, the length of this interval is nothing but b minus a, and this is always greater than equal to 0. Right? So the length is a positive quantity, non-negative quantity. The second thing is that length, if, as I mentioned earlier as well, okay, so suppose you have two intervals I1 and I2. Obviously the length of I1 union I2 is equal to the sum of each of the length of this, so is equal to length of I1 plus length of I2. Right? This is there when they are disjoint. So if I1 intersection I2 is phi, but when these are not disjoint, so suppose we have this I3 is there, okay, in that case length of I1 union I3, we can say it is nothing but the length of I1 plus length of I3 intersection with I1 complement, something like that, right? And in general what we can say, that length of I1 union I3 is less than equal to length of I1 plus length of I3. So this some bound we can get. Okay, so these three things are there when we are talking about the union of thing. Also if we take interval of this sort a comma a, so this basically is phi, in that case the length is 0, right? So the length of empty set is 0, I mean empty interval. So let me write more precisely in this way: a comma a is 5. Okay, so these are the three properties which you can see as of now, that these are there, and these are property you have already seen when defining the measure, right? This is already there. Okay, and what if some length of, so you already know this, all this thing as well. Suppose I choose some infinite length, so a infinity, then the length of this interval is nothing but infinity, right? For any a, whatever a you choose, for all a belonging to R, right? So this says that this length function can take infinity as well as its value. So the length function, if I want to write, so let us first make sense of what is the domain. So domain of L will be basically collection of finite union of intervals. Okay, so this will be the domain, and what will the range of L? So let us take any particular type of interval. So interval like, I am taking just open AB for simplicity. Okay, you can choose any of these sort of intervals. So I am taking those sort of collection of union of such intervals, and the range of L, okay, this will be it will be obviously greater than equal to 0, so it will start with 0, and it can take infinity as well, so it should be this sort of thing, right? So this is sort of the thing. Now if you see, you can show, you already know the notion of ring and subring, right? So okay, let me mention that as well. So ring is basically, which is, so this is, so it is closed with respect to union, okay, and closed with respect to, okay, so let me write it more precisely, that suppose you have some X non-empty set, and let R be any subset of power set of X, okay, then R is ring if it is closed with respect to union and with respect to difference. That means E F belong to R implies E union F belong to R. E F belong to R implies E minus F belong to R, right? And this R is sigma ring with, then this will satisfy the same property. Okay, so I'll just copy this. Okay, so what will be the difference? The difference will be, here it will be countable union. Okay, that is, if we have E1, E2, E3 till any one, then the union of all those sets will also be in R if each of one of them is in R. Okay, so this is the definition. So you can show that this will form a ring. Okay, so the domain of the length function is a ring, and the range is of this sort. Okay, so this is some way to motivate you how we should define the measure. Okay, so this is the measure, that if you take any ring, okay, one more thing that I said you here, close with respect to countable union, but that union should also be in the ring. Okay, so let me write it more precisely here. What this mean by what I mean by this, that, okay, no, that is always there, fine. Okay, yeah, okay, this is fine. Sigma ring closed with respect to countable union. Okay, so now we will define the measure. So suppose you have a ring of subsets of non-empty set X. So the function mu, which is defined on the ring R, from R to 0 infinity, it will said to be a measure if it satisfies the following properties. The first property is mu phi should be 0, and it should be countable additive, which means if we take a collection of EIs in R, and if all of them are pairwise disjoint, Now pairwise disjoint means EI intersection EJ is phi if I is not equal to J. Okay, this is what we mean by pairwise disjoint. Okay, so if it is pairwise disjoint and the union should be in R. Okay, now as I mentioned here, this R is a ring. If it was sigma ring, so this is obvious if R is sigma ring, right, because it is closed under countable union. So now we are saying, since R is the biggest possible domain where we can talk about measure, that is why we are defining on R. Okay, so if R is sigma ring, we don't need to write this assumption. So if we are disjoint and the union is in R, then mu of union should be equal to the sum of each of the sets, measure of each set. So these are the two properties of the measure. I mean, for defining measure we need these two property, and it is a non-negative function and it takes value in extended real line system, which is it can take value infinity as well. Okay, so this was all about measure. Now I'll list down some properties of measure, okay, which are as follows. That if you have two sets in ring, so suppose you have E and F, and E is contained in F, that means if E is this one, then F is something like this. Okay, then obviously since this is sitting inside F, the measure of E, the size of E should be less than equal to size of F. So this is one property of measure which is called monotone property. So everything you see is very natural. Okay, so far it should have subtractive property, that if E is contained in F, then the measure of F, okay, so the measure of F, which is the measure of the biggest set, should be equal to the measure of E plus measure of F minus E. So what is F minus E? F minus E is this one. Okay, so this should also be true, right? The measure of F should be the sum of these two, I mean areas basically, or the sizes. So this is there. This is what we mean by this subadditivity property, subtractive property, sorry. But the point is, why subtractive means basically that suppose this mu of E is finite, it is not infinite. In that case we can take this here and so the measure of F minus A, which is this violet region, yeah, so this violet region, the measure of this should be the measure of whole F, and if we subtract the measure of F with respect to measure of my E, then we should get this measure of this violet region. This is what it means. Why we are taking this condition? Because if suppose this is infinity, mu of F is infinity, and this is also infinity, then we cannot make sense of infinity minus infinity, right? This not sensible. And this is why when the measure is finite, then only we can take it to the left hand side. Okay. So this is another property which is also very natural. Now the third property is subadditivity, which means if you have any collection of these subsets, which is EI, any infinite or finite sequence in R, then and if E is subset of this thing, okay, E can be equal to this as well. In that case, the measure of E is less than equal to the sum of measure of EI. Now here you see this EI need not be pairwise disjoint, and that is why this inequality comes up. If it was disjoint pairwise, then this will be equal if E is equal to this. So if E is equal to this, this will be equal to this under the condition that EIs are pairwise disjoint from the definition. Okay, but here we don't assume that thing here. And this is also something natural. You can see that suppose this is E1, suppose this is E2. Now when you talk about the measure of E, so E is E1 union E2. In that case, see, this middle part is being counted twice. I mean, it's just counted twice when we take some of the individual thing. Okay, so let me color it. So suppose this is there. Now the measure of E1 is this one. and the measure of E2 is this one. So this region is being counted twice, and that is why that thing is greater than equal to the measure of the union. Okay, so this is also very natural. Okay, now the fourth property says that if E covers this union and these are pairwise mutually disjoint. So mutually disjoint is same as saying pairwise disjoint. So when these EIs are pairwise disjoint, then union of this is less than is equal to is sorry, if it is contained in E, then the sum of measures is less than equal to this. And this is quite natural. I mean, you can prove it very easily. So suppose this is there, then by the property A, you have that the mu of union of EI is less than equal to mu of E. And the moment you say these are pairwise disjoint, you can write it as summation of EI. This is this. So this is just by, so this is by A and this is by definition, right? Since they are, so this is there. Okay. The other property is the continuity from below. Now you have seen these things. Now first you should understand why we say continuity, why suddenly continuity things appear here, right? And then will make sense why we are talking about below. So let us first try to see the statement, what it says, that EI be an increasing sequence. So suppose this is E1, suppose this is E2, suppose this is E3. Okay, this is what it means by increasing, and it goes like this. Now suppose we are just talking about 3 sets. So for now let us restrict to 3 sets. Now if you take union of E1, E2 and E3, this will be E3, right? And so the measure of union of E1, union E2, union E3 is equal to the measure of E3, right? In fact, it is true for any finite collection, right? So what, let me write it more generally. It says that the mu of union of EI, I from 1 to n, is equal to mu of En, just because it is increasing. Okay. Now what this thing is saying, that take limit n tending to infinity. So if I pass take limit n tending to infinity, mu union I equal to 1 to n E of I is equal to limit n tending to infinity mu of En, right? Now what this is saying, that you can actually take this limit inside this mu function. So the moment you take this inside, this is what continuity means. If a mu is continuous, you can take this inside, and the moment you take this inside, this instead of n, it will be infinity. So when you take this limit inside, you will get this as infinity, and this is possible due to continuity. So this is the reason why we say this statement as continuity. And now why from below? You can clearly see why from below, because from down we are going upwards in this sense, right? So that is why it's from below. In a similar way, here we are coming from, from upwards. So the things are decreasing. So this is, let's say, E1, then this is your E2, or let's say E3, this is E2, this is your E1, okay, and this is how it goes on. Okay, and here also you can see that E1 intersection E2, so mu of intersection EI, I from 1 to n, is basically the measure of En. Okay, and in similar reasoning, we will say when mu is continuous, you can take the limit inside, and this is what you get. Okay, so this is why this statement is called continuity from above. And when we are talking about these things, we need the measure of sum of the ENs should be finite. Okay, this is very much required. Without this, you cannot say. You can see the counter example. Okay. Okay, so I will leave this as an exercise. So what you can do, construct En You can see in real line, I think, in itself. So construct En such that measure of En is infinity for all n, but intersection of En is phi. If you can construct such thing, okay, then the measure of this intersection is 0, but this will be infinity, and this will contradict your, I mean, not contradict, but this is a counter example when you don't assume this condition. In that case, this equality does not hold. Okay, so these are the properties of measure. Okay, so do you have any doubt so far? So what I have done till now, I just give you the motivation why we need the concept of measure, and then I have just introduced what measure is and some properties of measure. Okay, if there is no doubt, we can proceed further. Okay, so far what you can keep in mind, so far as of now you have seen just one example of measure, which is the length function. Okay. Now the thing is, what thing comes up, that we want to extend measure. Okay, now why extending measure? I'll tell you a few, I mean, the motivation behind extending, I mean, why we are suddenly extending measure. We have a measure, why, what we mean by extending it, and why we want it. Okay, so okay, so far what you have seen, that the length function is a measure. Okay, and the limitation of this measure was that can only measure the length of interval, can only measure intervals. Okay, so finite union of intervals, let me write in this way, intervals. Okay, this is what we can say. In fact, we can do it for infinite union of intervals as well, but so far, okay, so the main thing is that we can just measure some union of intervals, that's it. So this q intersection 0 1, this cannot be measured by this length function, right? So what we do, so using this length function, so this is the reason why we want to extend it. So what by extension mean, that okay, this was restricted, so the domain for this length function was this one. Okay, so the domain for this was just the collection of intervals, union of intervals. So what we want to do, we want to extend the domain of the function. Okay, so from here our goal would be to get some other L bar, okay, whose domain is D from 0 infinity, okay, is a measure. That is, and this D contains this union of intervals. So this union is contained in D. Okay, so this is just the main reason why we want to extend this measure, and this is what we mean by extending the measure. Okay, so from now onwards, the measure what we consider will be called pre-measure. Pre-measure means we are knowing this measure, and now we want to define some measure with a bigger domain, right? Okay, so the first step towards extending measure is to define some outer measure, and how we define it and what it exactly is, we'll see now. So suppose you have a ring R and you have a measure given on it. So you have R and mu. Okay, this is given to you. In this length case, you have been given this union of interval is a ring, finite union, and this L is the this measure mu. Okay, so you can consider analogous to this. I mean, this is in abstract sense. I mean, and this is an example of this one. Okay, and this example will lead to Lebesgue measure. So this L bar is nothing but Lebesgue measure. So let me write, this is Lebesgue measure. Okay. So this you will see. So okay, so for now we'll just we will not worry about this what measure is mu is. We'll just consider it is any measure which is given to us with the domain R. Okay, okay. Now when we, the first step would be to, from here we would like to go to hereditary sigma ring and then outer measure. This would be the first step, and then we will go to constructing the measure. Okay, so what is hereditary sigma ring? So hereditary sigma ring basically means it is a sigma ring, and the other property is, so this is the first property. The second thing is that if something belong to this H, then the any subset of this should be in H. Okay, so if E belong to H, the power set of E should be in H. This is what it means by hereditary sigma ring. Okay, okay, and okay, why we are introducing this? Because you will see the measure what we will construct, because from here we will construct some mu bar. Okay, so you will see that this mu bar will be complete, and that is why we are dealing with hereditary sigma ring. There is nothing special about this. The only benefit will be that the measure what we will get will be complete because of the sigma ring. Okay, that you will see later on. Okay, now this H of epsilon basically denotes smallest hereditary sigma ring which contains E. Okay, okay, now you see this one. This property is very much important for defining outer measure. Okay, that is why I have included it here. So what it means, you consider this set, collection of subset of X such that E can be covered by finitely union of members of E. So that is E, any E belong to this set means E is subset of union of EI, where EI belong to this epsilon. Okay, so such thing has been kept here on the right hand side. Now you can clearly check that this is a sigma ring. I mean, in fact you can show this is a hereditary sigma ring containing epsilon, and this we know this is the smallest hereditary sigma ring which contains epsilon. That is why this inequality, this inclusion holds. Okay, so this is one property which will be required for defining outer measure. Okay, now what are the properties of, I mean, how to define this outer measure? Okay, okay, so a non-negative function mu star. Okay, again non-negative, and it is in fact the range will be extended real numbers. Okay, that is it can take the value infinity as well. So it is called outer measure if mu star of phi is 0. Okay, and if E f belong to H with E contained in F, then mu star of E should be less than equal to mu star of F. So this is monotone property. So this should be there, and it should be countable subadditively. That if you have a collection of EIs in H, then the measure of union should be less than equal to the sum of the measures of each of the set. So these are the three properties of the out. I mean, not just the properties. These are the three things that we need, that mu star should satisfy for being an outer measure. Okay. Okay. So now let us, using this known measure. So this is how we extend. So as I mentioned earlier that you have mu, and for that you have domain R. So this is known to you. Known from here. So this is known. From here I would like to define this mu star, and the domain of this will be H of R. Okay, that is the hereditary sigma ring generated by this ring R. Okay, so how we define that? So this mu star, so this is what I have written. So clearly this mu star, this HR contain R, right? This is just by definition. So how we define that? So as I mentioned earlier, that H of R will be contained in E, will be contained in this set E subset of X, such that E is covered by union of elements of R. Okay, union of elements of R. Okay, this is already there. So now when we choose any element E from HR, I can write this element as I mean it can be covered by elements of R. So E can be covered by elements of R, right? Now each of the cover I will have this series. Okay, now I am taking infimum of such values. So suppose E has a cover E1, E2, E3 till E5, and suppose has another cover F1, F2, F3. So I'll add mu of E1 plus mu of E2 plus mu of E3 till E5. Okay, and then again I'll sum up mu of F1 plus mu of F2 plus mu of F3. Whichever will be smaller, that will be defined as the mu star of E. Okay, so it is infimum of sum of measures of covers of E. So you see, to define this mu star I am using this mu. Okay, and this can be proved that this mu star is a measure, outer measure. Okay, now I was saying that I am extending it. So mu is being extended to some other function. So clearly you can see that HR is containing R. That means the domain of mu star is large. So R is contained in HR. So the domain of mu star is larger. That is one thing. But if you restrict to R, okay, so if you take any element E in R, mu star of E is nothing but mu of E by the definition, how we define it here. Because only cover of E is E. I mean singleton E is one cover of E, and that will be the minimal possible value that any cover can take. Okay, so mu star of E will be nothing but mu of E. So this is why we say that it is an extension. So mu star is an extension of E. Mu star is an extension of mu, and this is an outer measure. So mu star is not a measure. Okay. Okay. So let me tell you here. So what we had this R. Okay. We had a measure on it. Now what we did, we defined H of R, and we had an outer measure on it, right? Now the point is, you will see later on that this all the elements of this cannot be measured. Okay, so what that measure thing means, that will be in the next slide. Okay, so for defining the measure, now what the the next step should be that I want to find the measure. So from here I will like to deduce some mu bar. Okay, and what will be the domain of this mu bar? That is the question. So you will see that the domain of mu bar will be strict subset of this HR. Okay, so this will be, let's say this is space of measurable subset. Okay, which can be measured. Okay, you will see that there exists some non-measurable set, that is we cannot measure that. Okay, so what our next step is to determine. Okay, so the next step, to determine what sets can be measured. Okay, now suppose this is the set which can be measured. I mean the sets which can be measured is this one. The moment, I mean measure, I will define what it means by measure, but suppose this is the set which can be measured. The moment you determine this set, now the mu bar on this set is nothing but mu star. Okay, so this outer measure becomes a measure if you define it on a proper domain. Okay, so this mu star will be a measure on a subset of this HR. Okay, that is the whole thing. Okay, so let us see how to define this. Okay, so now our goal is that I'll use this mu star to define a new measure mu bar. Okay, so this is what we mean by measurable set. So what we are doing, a set E is said to be mu star measurable if mu star of A is equal to mu star of A intersection E plus mu star of A intersection E complement for all A in HR. What it basically means, that suppose this is your E which is given, this is what you want to check whether it is measurable or not. So what you do, you choose any A in R, okay, and you see this A intersection E and A intersection E complement, which is this one. You check whether this identity is satisfied or not, that the measure of A should be equal to the measure of this one plus this one. If this is true for all A, then we say that E is measurable. So what we are doing here, we are partitioning this A in A intersection E union with A intersection E complement. Okay, this is how we are partitioning it. So clearly by subadditivity this is always true. Okay, by subadditivity this is true, and if you can prove this one, then it is measurable. Then E is called measurable. Okay, now okay, so let me add one more page, or let me put it here. Okay, now what I want, so this is one definition, right? This you can clearly see that, okay, this is a definition. Now why just this sort of partition we are taking into consideration, right? We should wonder like why we are dealing with this one and not the other way around. So you could have chosen some other method also to define this partition, right? Now suppose, so here you have chosen this partition. Instead of this, what if you write E? So what I mean to say is this one. So instead of partitioning this A, you could have partitioned this E. So this E, if I partition in this way, E intersection with A union E intersection E complement intersection, no, E intersection A complement, I will say. So this is another definition what I am trying to define. So E is measurable if mu of E, okay, so if mu of E is equal to mu of E intersection A plus mu of E intersection A complement, right? By looking at it, it seems that this should be also satisfied. This definition is very much natural, this one. In the same sense, this also looks very natural, but this, why we are not taking this as the definition, right? You can think that, we can also choose this definition, but the point is, suppose E is non-measurable. So notice one thing, that this is always true. So this is always true, right? Now I am choosing E non-measurable, okay, and mu star, okay, so why I am writing mu here, it should be mu star, okay. And suppose that mu star of E is infinite. In that case, this identity always hold. So this is, let's say, star, then a star is true, right? Because this is always true, and this side, since this is infinity, everything I can write infinity greater than equal to anything, whatever it is on the right hand side. So star is always true. So how it can define E to be measurable, right? So this definition is wrong. This cannot be a definition. Moreover, you can try with other thing as well, okay. You can try with some other definition as well. So what you can define, okay, this is one way you can think of. What else you can think? Okay, this is only way. So these are the only two possible ways to define that. So either you partition A or you partition E, and this partition cannot, this sort of is not helpful, that we can see from here, right? Okay, so this is the reason why we define in this way, that E is measurable if for each a we can partition it properly. All a what we choose, such thing should happen, that mu star of a should be equal to a intersection e plus the measure of a intersection e complement, outer measure of that. In that case we say e is measurable. Okay. Okay, so now what we do, now we are doing nothing, it's just the same story. So now we define S bar as a collection of mu star measurable sets. Okay, now okay, so this is subset of HR and this is moreover is a sigma ring. Okay, so this S bar you can check that this will form a sigma ring. That means if you have E1 till, I mean if you have this collection EIs, each is measurable, then the union of EI is measurable. Okay, this you have seen in the lectures, I guess. And if E and F are measurable, this would imply E minus F is measurable, and so it will form a sigma ring. Okay. Okay, so this forms a sigma ring, and this is another property which you have seen. This is required to prove that this S bar is a sigma ring. Okay, so it basically means that if you have a set A, okay, whatever set you choose from the sigma ring, if you intersect with union of EIs, and if you take the measure of this will be equal to the sum of measure of I mean outer measure of A intersection EI. Okay, so these two properties are there. For now we are just concerned about this one. Okay, that S bar is a sigma ring. So on this S bar we define this mu bar, and which is given by this, that mu bar of E is nothing but mu star of E. Okay, so again let me complete the story again. Okay, I think this is the end of the theory part. Okay, so this was given to us RU. From here we define this H of R with mu star. This mu star was outer measure. Then we find, okay, so this can never be equal to, okay, you will see later on that all HR function cannot be mu star measurable. So this means that there will be some gap in these two things. So this is S bar, and with this S bar mu bar comes up, and mu bar is nothing. So in this region, mu bar is equal to mu star. Okay, so this is how we construct the measure. So this mu was pre-measure, pre-measure means it was given to us, and from there we constructed mu bar. Okay, so that was the whole story about this measure thing for the first week, what you have seen. Now let us quickly see these exercises. Okay, so let us start with this first exercise. So what it says, that suppose you have, this is the solution, suppose X is n and R is given to be the collection of finite subset, collection of all finite subset and their complements. Okay, so this means E is subset of n such that E is finite or their complement. So it is basically equivalent to saying that E complement is finite. Okay, so you have to check that this R is an algebra. Okay, so what algebra means basically, so what we need to make sure, the first thing is that X should belong to R. This is the first property of algebra. The second one is that if A, B belong to R, this should imply A union B belong to R. Right? This is the second property. The third property says that if A, B belong to R, then A minus B should belong to R. Okay, this is the third property. Okay, so let us see this one. So X belong to R, basically is it possible? We know that the X complement is phi, right, and this is finite. So X is there. Now suppose A and B both belong to R. Okay, so they are so suppose the first case, that A, B belong to R means suppose A is finite and B is finite. If both are finite, this would imply A union B is finite, right? The second possibility is, suppose A complement is finite. Okay, then what you can do, this implies A union B whole complement. If you do, you will get A complement intersection B complement, and this is subset of A complement, and this is finite, so this is finite. So this implies A intersection, A union B complement is finite, and hence we are done, right? Because here we consider both the cases. Let me see. So if A is finite, one case is missing, so there is another case. So suppose A is finite and B complement is finite, right? So this is the another case. Now when this is there, you consider this again the same thing, A union B complement. If you do, you will get A complement intersection B complement, which is contained in B complement. This is finite, so this is finite. Okay, so in all the three cases we got that this A union B will belong to R. Similarly, we can deal here as well. So suppose A B belong to R, we have to show A minus B belong to R. So the first case, let us assume that A is finite. Okay, so A is finite. When A is finite, A minus B, okay, is nothing but A intersection B complement, and this is subset of A, right? This implies A minus B is finite. Okay, the second case would be that A complement is finite. This would mean that A minus B complement, which is A intersection B complement whole complement, which is A complement union B, okay, and A complement is finite. Also you can assume B is finite, okay, because the B finite and infinite, B finite, B complement finite has been considered here. So let us assume this as well, B finite. Okay, now the moment I say B finite, then this is finite, this is finite. I think this covers all the cases, because A finite, B can be anything, okay, A complement finite and B complement finite. Okay, there is one more case which is left. So where should I write? Let me write it here. Suppose A complement finite, I think it should be done here, B. Okay, let us see, B complement finite. Okay, if this is there, A minus B, okay, which is A minus B. If I do, I will get A complement, A intersection B complement. Okay, obviously. So I will get A intersection B complement, that this is subset of B complement. So this is finite, so this is finite. Okay, this implies A minus B finite. Okay, so these cases can be, in the same way we can do these two things. So it's just some simple checking that we need to do. So, and hence, since all these properties hold, this R is an algebra. In the same way, we can deal with this question. Okay, so it exactly the same argument it uses. So you have to prove that R is a sigma algebra. Okay, so let us see. So sigma algebra, the first thing what we need to make sure that X should belong to R. Okay, what this R is, so I have not said this. So R is nothing but the subset of X such that E is countable or E complement is countable. Okay, and then you have to prove that this R is a sigma algebra. So if you see this X complement, this is nothing but phi, and X is uncountable. Okay, so we cannot directly say that X is countable, so X belong to R, but we know that the X complement is phi and this is countable, so X belong to R. Now choose E and F in R, and you have to make sure that E minus F belong to R, right? So E minus F is nothing but E intersection F complement. Okay, so if E is countable, consider the case when E is countable. In that case, E minus F is subset of E, so this is countable. I mean, this is countable. Okay. Now consider the second case when E complement is countable. Okay. So E complement countable and F. Okay. So F you assume to be countable. Okay, in this case, E minus F complement, if I do, I'll get E complement union F, and this is countable. Union of countable set is countable, so I'll get this is countable. In the third case, when E complement F complement both are countable, in that case again E minus F, since it is subset of this F complement, so this is countable. So E minus F is countable. So in all these possible cases, we get that E minus F belong to the sigma algebra. I mean belong to R. So this property is clear. Now the last property is, suppose we have EI in R, you have to prove that the union of EI is in R. Okay. So suppose the first case, when all EI are countable. Now this would mean that the union of EI is countable. Why? The reason is simple, because the countable union of countable set is countable. So this is there. The second case is, suppose one EK complement is countable. I mean this is not true, that all EIs are not countable. Okay. Now when some EK complement is countable, this would mean that union of EI, if I do and I take the complement, this will be intersection of EI complement, and this is subset of EK complement, right? And since this is countable, this would imply that union of EI complement is countable, so this complement countable, and so I mean this union of EI is also in R. Okay. So this proves that this R is a sigma algebra. Okay. Okay, I hope it's clear and everything is fine. Okay. Okay, now let us proceed to the next problem. Okay. Suppose R is any sigma ring that is given to you, and you define this S, which is E is subset of X, such that E intersection F belong to R. Okay, for all F in R. If this is there, then this is the set S. You have to prove that this S is a sigma algebra. So the first thing is that you have to prove X belong to S. Now why X belong to S? Because X intersection with F is F, and for all F in R, I mean, and this belong to R for all F in R, right? So that is why X should belong to S, because its intersection with each element of R is in R. Okay. The second thing is that if AI this belong to S, then you have to show that union of AI belong to S. Okay. So union of AI belong to S means if I intersect union of AI with any element of R, I should get it in R. So union of AI intersecting with F will be nothing but union of AI intersecting with each of, I mean F intersecting with each of the AIs, right? And this is in R since AI belong to S, and since R is a sigma ring, sorry, so the union belong to R. So this belong to R. Okay. The third point is that suppose A, B belong to S. Okay. You have to prove that A minus B also belong to S. How to do that? So suppose A B belong to S means, so let us see A minus B intersecting with F. Okay, now it's the same if we intersect A with F and then we subtract B intersecting with F. Now we know since A B belong to R, sorry S, this belong to R, this belong to R, and since R is a sigma ring, this belong to R. So this is also there. So it's easy, and it just, I mean, for checking sigma algebra, sigma ring, algebra ring, I mean, it's very easy. You just have to check it, I mean, manually, that by seeing how what could be the possibilities. Okay, so this is also quite easy. Okay, now this is quite interesting, and I mean interesting in the sense that it is useful in some of the things what you will learn later on maybe. Okay, so what it says basically, that suppose you have a sigma ring, okay, of subsets of X, and suppose you have a measure on this R. So for each, so you fix one E and you define some mu E corresponding to this E. How you define that? That mu E of A should be equal to mu of A intersection E. Okay, so it's like you have a known measure to you. Using that measure, you are defining another measure. Okay, but see here, the point is that both of the measures are on the same domain. So mu E is also defined on R, mu was also defined on R. Okay, so I mean the domain is same, but the properties will be a bit different. I mean the measure of some set with respect to mu will be different, and with respect to mu E will be different. So first see what it is doing. Okay, so suppose this is your set A. With mu you have the measure is equal to this thing, but with mu E, so suppose this is your E which was fixed, so this is fixed. So mu E of A will be just this one, this part. Okay, so this is what this measure is doing, that this measure is taking that part of the set which is intersecting with E. Okay, so it is just measuring the part of A which is intersecting with E. Okay, so this is the I mean the main function of what this mu E is doing to A. Okay, so you have to prove that mu E is a measure. So let us recall the first property. That the first property says that mu E of phi should be 0. So what is mu E of phi? Mu E of phi is mu of phi intersecting with E, and with is mu of phi, and we know that mu is a measure, so mu of phi is 0. Okay. The second property was that mu E of A should be greater than equal to 0. So this mu E of A is nothing but mu of E intersection A, and we know this mu is measure, so this is greater than equal to 0. The third and the most important property is that, not most important, but the another property, not property but the properties for defining the measure. Okay, so by the it's just the definition and not the properties. Okay, so what was the third thing which was required for proving something is measured? That countable additivity. So suppose you have AI pairwise disjoint. Okay, now you want to calculate this mu E of union of AI. Okay, I from 1 to infinity. Now by definition it is mu of E intersecting with union of to infinity AI. Okay, and this is mu of union of I equal to 1 to infinity E intersecting with AI. Now this mu is a measure, so and these are disjoint as well, right? Because this AIs were disjoint, so these are disjoint subsets. So this is nothing but measure of sum of I equal to 1 to infinity mu of E intersection AI, and this is nothing but mu E of AI. Okay, so these were the properties that were required to check that mu e is a measure. Okay, and this proves that mu e is a measure. Okay. Okay, so now let's move to the next problem. Okay, so let us first try to understand what this is saying. Okay, and then so you see what it's there. So you have been given a ring, again similar thing, and you, on a as a subset of this non-empty set X, and mu is a measure on R. Now you have been given that suppose E and F belong to this ring. So let me, by pictorially, let me make you understand. So this is your E and this is your F. What it says that the measure of E, so this is the measure of E, and the measure of F, this is the measure of F, okay, will be equal to, so this is the left hand side, so this is LHS, this figure, and what is RHS? RHS is, let me copy it. The RHS is the measure of E union F. Okay, so this is your E union F, right? So this was there. So when we do E union F, this will be considered once. So this is measure of E union F, and the measure of intersection would be this part. Okay, so this is this part. This is E intersection F. So you can clearly see that this should be true, that the measure of union of E and F plus the measure of intersection should be equal to this thing, right? Because when we consider the sum of the measure, this intersection part is being counted twice. Okay, so this is what this problem is saying. Now how to prove that? So this was the this was just to make you understand that this is something which is not very abrupt, it is coming naturally. Okay. Okay, so let us first try to prove. Okay, so when mu e, suppose mu of E is infinite, I mean any of them, or mu of F is infinite, any one of them is infinite, then obviously the left hand side is infinite, and also by sub-additivity this will be infinite, right? Because this is bigger than the individual set. So by monotone property, I mean this would imply that mu of E union F is infinite. So both side infinity, and hence it's done. So the interesting case would be to assume that mu E comma mu F both are finite. Okay. Okay, so let us first try to say this E union F. So E union F, I can write it as, so this is E union F, so I can write this as this part union with this F. Okay, so E union F I can write at E minus F union with F, right? So mu of E union F will be equal to mu of E minus F plus mu of F. Why? Because these are disjoint, so by additivity I get this. Okay, so this is one way to get some identity. Okay. Now why we are trying to do, we got this term and we got this term. Okay, now we want to look for this and this. Okay, so let us try to see what this E can be written as in disjoint format. So E I can write as, so I want to write in terms of intersection. Okay, so I can write E as E minus F union with E intersection F, right? This part is this part plus this part. Okay, so again by additivity I can write mu of E as mu of E minus F plus mu of E intersection F. Now you just substitute the value of from here to here or from here to here, anywhere around. So combining using 1 and 2, you will get star. You get star. right? That is trivial to check. So suppose you choose, I mean from here if you want to get mu of E minus F, that will be mu of E minus mu of E intersection F, which you put it here, then mu of minus of mu of E intersection F will be thrown on the left hand side, so you will get this thing. Okay. Okay, so this was with measure, okay, and this was the condition. I mean this is what we got. Now what if we do it, we want to do it with outer measure? Okay, so suppose now you have hereditary sigma ring, okay, and you have mu star, which is an outer measure on this H, and you have to assume that at least one of them is mu star measurable. Okay, without this is not true, and that I'll explain why. Okay, why we cannot expect such thing. So at first let us try to prove this part. Okay, so first, okay, so the first case again, assume mu star of E comma mu star of F are finite, because if both are finite, infinite, we will get again, I mean if any of one of them is infinite, we will get the identity. Okay, so we assume both to be finite. Okay, now assume, so you have been given that one of them is mu star measurable, so assume E is mu star measurable. Okay, I mean I should not try to assume, so let E be mu star measurable. Okay, now what does that mean? This means that, so mu star of A is equal to mu star of A intersection E plus mu star of A intersection E complement for all A in H, right? This is by definition. Very good. So now what you do in particular, choose A equal to F. Okay, so what you get is mu star of F is equal to mu star of A intersection F plus mu star of A intersection F complement. Sorry, what I am writing, F intersection E plus F intersection E complement. So this is one equality. Now again, so this is the first thing. Again, what you can do, you choose A to be E union F. Okay, so the moment you choose E union F, put it there, mu star of E union F is equal to mu star of E union F intersection E. So that will be E, right? Because we are E union F intersecting with E will be E, plus mu star of E union F. So let me write first, intersecting with E complement. Okay, so you just distribute it. So E intersection E complement will be phi, and then what you will left out with, F intersection E complement. So this is the second one. Now again you do the substitution, that mu star of F intersection E complement, you have from here you just find it will be mu star of E union F minus mu star of E, put it here, and then you throw mu star E here, you will get this identity. Okay, so you got the result. So use again by 1 and 2 we get hash. So this is hash, let's say. Okay, so this is what you I mean this is how you can prove this one. Okay, now as I was explaining, that you have to assume at least one of them to be mu star measurable. Okay, yeah, so suppose E, F are not measurable. So I am considering this case. Okay, E and F are not measurable. So, and in particular assume that these are disjoint. Okay, so from here, from hash, what we get, so this proves here, this proof complete. This is just a remark maybe. Okay, so from hash what we get is mu star of E plus mu star of F is equal to mu star of E intersection F. Okay, now what does that mean? This implies that mu star is a measure, right? I mean, because if you see, the only difference with outer measure and measure was that outer measure was countably sub-additive, but mu star, I mean the measure was additive. So this means that mu star is a measure, right? And mu star is defined on HR to 0 infinity. That is mu star HR to 0 infinity is a measure, and this would mean that this all the elements of HR is a measurable function. This implies all elements of HR are measurable. Okay, but you assume that E and F are not measurable. I mean, and E and F are in fact members of HR. Okay, so this is in some way, this is a contradiction in that sense. Okay, so that is why you have to assume that one of them should be measurable, otherwise we can arrive at some, I mean, weird situations. I mean, this gives a contradiction basically. Okay, so that is why we have to assume that at least one of them should be measurable. Okay, yeah. So now let us see another property of which is called excision property. Okay, so what it says, that this is excision property of outer measure. So suppose you have a hereditary sigma ring and you have a that F here. So F is a measurable set of finite outer measure and E is containing F. So it's like this is your F, this is your E. Okay, this property is, as I mentioned earlier, that this is true for measure. This is one of the property of measure. Okay, so here we are trying to get the same property for outer measure, but the condition over here is that one of them should have this F should be measurable. So the one which is smaller should be measurable. So this is the condition which was not there. Anyway, when we talk about measure, everything is measurable. Okay, so here we have to put this condition that F should be measurable. That is the the one which is of a small size, that should be measurable. In that case, you have this relation. Obviously, the finite thing is required to throw this, to get this with minus sign. If we don't have finite thing, then this is always true. Mu star of E minus F plus mu star of F is equal to mu star of E. This is always true. Even if this is not true, then also this is true. Okay, so let us try to prove that one. So what is given to you, that F is measurable. Now this implies that mu star of E is equal to mu star of E intersection F plus mu star of E intersection F complement, right? And what is this mu star of E intersection F? Intersection would be F itself. So this is mu star of F, and this is E intersection F complement, which is this region. So this is another way of writing E minus F. Okay, and this is what we got. So we proved this one, right? This is called excision property of outer measure. Okay. Okay, so that's it for today. So this is all what I had to discuss. I hope you understood all the problems and all the theories what I have recalled, and you got the insight what I was trying to give you initially in the theory part. Okay, so if you have any doubt, you can ask. else we can stop here itself. Okay, if there is no doubt, we can stop here. Okay.